All right, today we're going to tie together a couple concepts. So nothing's really new today. I am introducing an equation. Those of you who took pre-AP have seen this equation. But now we're connecting thermochemistry to equilibrium. So right here, this equation is not the version that you're going to need to know or worry about, but I just want to explain it because it leads to the equation we do use a lot. This is an equation where if you take a delta G at standard conditions, so we figure out delta G, Big Mama or whatever, and we have a reaction going, and we do something to mess up the reaction. We either change temperature, or if it's an equilibrium system, we may change the concentration of some of the reactants, or we may change the pressure of some of the reactants. And in the process, that is going to change, with this correction factor, what the actual free energy is. And so this is how to find the delta G when we're not at standard conditions. So when we're not at standard conditions, we would have to use this equation. That equation is not given anymore. It used to be. Now the only equation that's given is what we call the negative Ratlink equation. It's using the standard G to find K and vice versa. So this is at equilibrium. So what's the relationship? Well, here, when we are at equilibrium, we talked about this yesterday, what's the delta G of a system? 0. So the actual delta G of a system is going to be 0. If we put 0 in for this and then move RT ln of, because we're at equilibrium, Q becomes, what's Q at equilibrium? K. Q will become K, and we bring it over to the other side. That's where we get this. So this is just assuming standard conditions and assuming we have an actual K value. Now, people, I thought you said if it's at equilibrium, delta G is 0. Only delta G of the system. This is the standard delta G. So we're just finding standard delta G when we're doing this. Let's go ahead now and jump in and work some problems. Today's a quick day. I know you're sad about that. All right. Aw. Delta G for the reaction N2O4 going to, and it says delta G naught, so standard delta G at 25 degrees Celsius, was determined earlier. We actually didn't determine it earlier. It was one of the ones I skipped. However, because we're at standard, what would be the quickest way to find delta G? Yeah, we can do Big Mama, and I actually have the delta G values on the board. So delta G naught is going to be equal to 2 times NO2 delta G is 51.31 minus 1 times N2O4's delta G is 97.891. And these are all going to be in units of kilojoules per mole. So let's get an answer. I heard the 0.73. What was the first? 4.73. Does anyone else have that? Yeah. All right. So 4.73 is the delta G of the reaction. So is this reaction spontaneous? No. Currently, it's not spontaneous. It's standard conditions saying it's not spontaneous. So in our next step where we're calculating K, the energy R, 8.31, is in that, and that's in a unit of joules. So we cannot plug this delta G in as it is. So again, we're going to have to convert this to joules. So this would be 4,730 joules per mole. That's what we're going to plug into negative Ratlink, because we're going to use that standard delta G to find, I don't know why I put a 1 there. We're just going to, this is what I was saying, how I can't think today. This is exactly what's been going on all day. Negative RT ln of K. I always want you to make a prediction, because I feel like it helps you decide, does my answer make sense? Could I potentially have made an error? Our delta G at 4,730, you guys said, is not spontaneous, right? So if we're at equilibrium, if we're spontaneous in the forward direction, what would the magnitude of K be? That means the forward direction is favored, greater than 1. But in this case, we are not spontaneous in the forward direction, so the opposite reaction is favored. So what can we predict? Less than 1. So we're predicting that K is going to be less than 1. I want you to make that prediction so when we get your answer, we can determine if that even makes sense. So we're going to put down 4,730 joules per mole is equal to negative 8.31 joules per mole K times the temperature of 298 times the natural log of K. So let's go ahead and solve for that. This is hugely missed on the AP, that something about solving for natural logs. So you're going to take this number, 4730, divided by negative 8.31 divided by 298, set that equal to ln of K, and then e to that number will give you your K. So what did y'all get? 0.148. Awesome. 0.148, is that less than 1? Yeah, so I feel pretty good about that number. Okay, next then says, calculate the delta G for the reaction if the partial pressure of N2 is 0.1 and the partial pressure for N2O4 is 1. Uh-oh, what we did was we took it out of standard conditions by doing that. What's standard pressures supposed to be? 1 atm. So we're not at standard condition anymore. Our delta G naught is not good at this point. So we're going to have to use that equation from above. I'm not going to be super concerned about you doing this. It's probably not going to be tested. So I'm just doing one so you can kind of have some experience with it. Delta G naught plus, it's RT ln of Q. All right. So we are going to, let me turn half the lights off because it seems like my bulb is getting less and less. We're going to use the delta G naught and adjust it. So our delta G naught, again, we have to have it in joules, and we did calculate that. So delta G naught is equal to 4730 joules per mole K, plus R is 8.31. This is joules per mole. I don't know what's going on in my head. Joules per mole K times, did our temperature change? No, they didn't give us a temperature change. They did, though, give us a change in our concentrations. So now we calculate Q, which is just K, the K ratio, using the pressure. So it's not a concentration K, it's a KP, so, or QP. We're going to put the Q values in here. What do I put on top? I'm doing a K. NO2, and what do I do to that number? I square it because it's squared in the equation, divided by 1 to the first. So we're going to see what this does to the spontaneity of the reaction. It's currently, at standard, it's not spontaneous. Now that we futzed with the pressure, it might become, and it might not. We'll see. Those of you who aren't calculating, you think it's just, oh, I can calculate on my own. You really should practice it. What did you get? So negative 6,680. Is that a good answer? Negative 6,674 joules per mole. So pretty much everyone got the second one? 6674? Oh, instead of 8.3 and 4? Okay, that's fine. And therein lies the difference. Like, that's really crazy, the little amount that can change it. That's why you have to show your work. Because if you just, let's say, Rui was actually right using 8.31 because on the AP, that sheet, it's only 8.31. So I suggest using the constants and any value they give you, a voltage, a delta H, whatever, exactly as it is on the sheet, because that's how the rubric is built. So I'm not saying you won't get credit, but I'm saying at that point, if you use 8.314, it's even more crucial that you show your work. Because if you just had your answer, they're like, nope, that's off, They won't know that it's because of that. So you always need to show your work. So you're saying you used 8.31, Rui?
No, I used 8.14.
Okay, so you were wrong. Everyone else was right. Got it. So scratch that, reverse. Rui was wrong.
Yeah.
Okay. It's okay. He showed his work, so he'll be fine. So looking at this now, we went from non-spontaneous to pretty dang spontaneous. Let's see if it makes sense in terms of chemistry. At standard conditions, our NO2 and our N2O4 would have been at 1 atmosphere. So if we're not at standard conditions now, it's because NO2's pressure was decreased. If we decrease the NO2 pressure, essentially removing NO2, taking away moles, what happens? This is supposed to be an equilibrium system. What happens in terms of Le Chatelier's principle? It's going to do what? It's going to increase the pressure of NO2 by doing what? Shifting hard right. What does that do to spontaneity in the forward direction? Makes it spontaneous, and that's why it works. Okay. So again, I just really like you seeing how the numbers match what we have just through conjecture is believed to be true. Okay? All right, let's do the next one. All right, consider the reaction given. The concentration equilibrium constant, Kc, for this reaction is 1.12 times 10 to the negative third at 750 Kelvin. What would you expect this value, or would you expect this value to increase or decrease at 300? Explain your answer with no calculations. So the first thing is we've kind of done problems like this before where we've tried to figure out whether something is going to occur with a change in temperature, but what did we have to know in order to determine what effect a change in temperature has on an equilibrium system? So, but what about the enthalpy? Exactly. We need to know if it's exothermic or endothermic first. That's the first order of business because we can't predict any shift. So I'm sure you're looking at going, I just want to solve for delta H real quick. No, we can't do calculations yet. So just look at that reaction, and you got to open your brain a little bit and ask yourself, does that resemble anything I know? Is it something forward? Is it something reverse? What is that, Rui? It's kind of combustion, but what kind of combustion? Is it combustion forward direction? It's like a reverse combustion. Do you see that? Combustion reactions are always exo, but this is reverse, so this is endo. So we're going to predict that this is endothermic. If this is endothermic, what side are we going to write the word heat? Here, on the left. So if it's endothermic, heat goes there. Now the question is, what happens from 750 to 300 in terms of the K? So if we go down in temperature, if we remove heat, which way does that reaction shift? Reaction shifts left. If the reaction shifts left, what happens to K?
Goes down.
Does everyone see that? K decreases. So that is our prediction. We're predicting K is going to decrease. So now we're just going to take a few minutes and mathematically prove that to be the case. So first thing we'll have to do is calculate the delta H and the delta S reaction from our values. So I'm going to do a little bit, start up here some, just because I don't have enough room down there. So delta H is equal to, we have everything on the board for Big Mama. This is going to be a long one. 4 times HCl is negative 92.307. O2 doesn't have an enthalpy. Products minus reactants, so we only take into account the water gas. Water gas is negative 241.818. Is it 241 or 214? Okay. Okay, so this will come out to be what in kilojoules per mole? Got to make sure to do this right because it could affect our final prediction, and I don't want to get that wrong. Anybody? 114 point what? I'm hearing a lot of other things. Did more than one person get .408? All right. So 114.408. I can kind of predict what's going on here. If we're finding K, don't you think at some point we'll probably have to use RATLink? So that's probably going to need everything to be in joules because of the R constant. So I'm going to go ahead and convert this to joules now. 114,408 joules per mole. Okay, so that's my delta H. So now let's do our delta S. Delta S is going to be equal to, this is going to be a longer one because we have an S for everything, 4 times 186.908 plus 1 times O2 is 205.138 minus 2 times Cl2 is 233.066 plus 2 times H2O gas, 188.825. So what is our delta S value? 108.998? 988? Want to get a second on that? Okay. Joules per mole. You're banned today, JD. You can put away your calculator for the day. I'm kidding. All right. So there's our delta H and our delta S. And we did what we were told. So now let's go on to part C. Part C says, using the values obtained in B, calculate the delta G for 300 and 750. Well, I don't really see the point of calculating it for 750. Why would we need it for 300? Because we need to then use it to find K, right, at 300, because that's the one we're trying to compare. So I'm going to adjust this problem and just say we don't need to find it at both temperatures. There's 0 point to that. So delta G is equal to, ghetto homies. So we're solving for delta G. Someone tell me the delta H in joules. I don't want to go back. The temperature is, we're trying to find it at 300. And then what was the delta S? Okay, so what is our delta G value in joules? So 712? 81,712 joules per mole. All right, so that is our delta G. And is that the correct sign? It's not negative or anything. We're good. All right, so now we're going to calculate the Kc and see if our prediction was correct by doing what? RATLink. So I have my delta G is equal to negative RATLink. If you look above the board, RATLink, there's 2 rats. See their tails are linked? Okay, RATLink. Way up high, above the little kids. Those are, there used to be a band, I don't think they exist anymore, in Austin called Ritalin Kids. And so Ritalin kids was another way to, all right, but it's negative rattling, so don't forget it's negative rattling. But it's on the AP sheet, so whatever. Minus 8.31 joules per mole K times the temperature of, we're predicting K at 300, times the natural log of the K. So we predicted a decrease, right? And what, I need to go back. What was the K at 750? Times 10 to the negative third. Thank you. So that is our Kc at 750. So we predicted a decrease. Yep. I remember the negative 15 part. 5.83. Did it decrease? Oh, I quit. Did K decrease? Yes, it did. It decreased quite a bit. So our prediction was correct. There's no units. I have to take the units off too because it's not delta G, y'all. I told you from the start, I think it's a self-fulfilling prophecy. I told you today my brain was not functioning at appropriate levels. So that's it for the day. I'm going to hand you back your tests, and you can file those away and just start test corrections later.